So this is just a quick reminder on what the rectangular method is. It's basically just a Riemann sums from calculus. So say we have some curve f of x that we are trying to take the integral of. So what we want is the integral. We're doing a definite integral from a to b of f of x dx. Let's say that f of x is just a function that we can't directly integrate. So an example might be like f of x equals x times tangent x, so you can't directly integrate that. But for the example here, we'll just use something simple, and we'll just say that this is from a to b here, right? And in this context, we might actually be a little bit more formal and just say we're going to start at x0 and we'll end at xn, right? But this is from a to b, and what we'd like to do then is break this guy up into intervals, just like we did with Riemann sums, and we can approximate this function with just a series of rectangles, right? And so we can say, okay, this is a rectangle, and this is a rectangle, and this guy, and this guy, and kind of this guy as well. Now, obviously, we can see that some of the areas don't match here, right? So we're going to have, this is below the curve, so we're going to be missing some area here. And then in other portions, it's above the curve, so we're going to get a little extra area in here. The rectangular method is not the most accurate, but it certainly will do the job. So now how do we build this then? Because we'd like to actually add all this up, right? So we can add our additional indices, our x's here, so that's x1. That's a terrible one. Try that again. x1, x2, and it just goes all the way on to xn. I guess we could call this xn minus 1 here. And then we also have where the function is evaluated. So you'll see right here, this would be f of x0. This is f of x1, and so on, all the way to f of xn minus 1. Or sorry, this is f of xn. The one before it would be f of xn minus 1. And so now we just need to calculate each individual area, right? So if we want to calculate the area of this rectangle, we just need base times height. And so the base is just x1 minus x0 times the height, which is just the f of x0. And then we need to add this next rectangle. So it's x2 minus x1 times f of x1. And we just keep doing this all the way until the end. The very last one is xn minus xn minus 1. And we multiply that by the height of the function here, which is f of xn minus 1. Notice we don't use this last value here for this particular application of the rectangular method. And what's nice is that each one of these guys is actually the same value, right? It's this width here, delta x. We kind of decided that based off how many blocks we broke this up, right? So there's the first block, the second block, on and on and on until the nth block. And basically the size of each one of these, this delta x, is just b minus a divided by the number of approximations that we want, right? And so I can pull all this out front, right, and call it just delta x. And of course we know that that is just b minus a over n. So really what I want to do is I want to take b minus a over n, right, and multiply that by the sum of all of these f of x's, right? And so that part we need to be a little bit more careful about in our notation. So I'm going to say that this is f of xi, right, where x is just the ith element along here, and then we'll index it. We'll say something like, from 0 to n, from x0 to, well, I guess in this case it would be xn minus 1. And so that right there then is going to be, well, we'll do a little approximation. Our approximation for the integral of f of x dx. And of course, the larger we make n, the more accurate we hope to be here. And so this right here is what we should be coding up for the rectangular method.